So good afternoon, everybody. I know it's late in the day, but I am going to try to show you some actual code. Have you seen any code today yet? Real code, actual code? In an IDE, somewhat? I'll try to show someone. And even if I have the time, I'll try to type something in as well. It depends on how fast we go, right? So I'm going to talk about a subject that is actually very tiny compared to most of the other subjects that you'll see today and tomorrow. It's going to be about monads. Now, some of you might be wondering, what on earth is a monad? So I'll try to do that talk. I'll try to explain it, right? So what is a monad? I'll do that. And according to Randy, you should never use them then if there's a what is section in it. But in this case, I might say it's an exception because it's very likely that you are already using monads in your code. You just don't know, probably, right? So that's a big difference, I would say. So if you don't know what it is, stick with me. I'll try to explain it to you. The only problem with monads is, as soon as you understand what they do, you won't be able to explain them anymore. That's not that's by Douglas Crockford, he said that, but I'll try and explain it anyway. So, and I'll show you some code. So just a show of hands, who of you is actually writing code? Cool, so that's most of you. Who of you? So I have code examples in 3 different languages, Java, C#, and TypeScript, which the last one is my personal favorite currently, so I'll probably be typing that. So, not to waste any time, this is me. I'm basically a dad. I brought one of my kids here, and he's now totally bored in the hotel room because the weather sucks. And I brought him last year, and the weather was much better. So I'm a dad, I'm a software architect, I'm an independent consultant, but I don't like the word consultant, just as I don't like the word resource. So I write code, I speak about it, I write about it. Currently, one of my assignments is to be the CTO of a company called Anva, which is in the Netherlands, and I don't know if you saw Kim's talk just before in the other room. She's the head of IT at the company that I'm the CTO for. So, and I used to be the CTO of an insurance company before that, where Kim also was head of IT. That's not a coincidence, by the way. And before that, I used to be the global agile thought leader at Capgemini, whatever that may be, right? So, it basically allowed me to fly around the world and do funny stuff and talk to people. And this is my website, my Twitter tag, my GitHub account, which is barely anything in it. I should be putting in there more. This is my email address, doesn't really matter. Nobody uses email anyway. So this is what I do. Just to give you a short example, I used to work for, I did a project for the Social Security Agency in the Netherlands. They wanted to get rid of their COBOL. They had like 20 million lines of COBOL in their systems, and they want to get rid of it. Didn't work. Of course, the government spent 225 million euros on that, and it failed miserably. And then they said, could you build a website on top of it that does basically the same? We said, yeah, we can do that. So I wrote a bunch of code in there, and to show you the work I do, basically, one of the project managers came up to me and they said, could we do a demo to the CEO of this institution? I said, sure, but there's some untested code in there. And usually I was actually trying to write some code to prevent people from moving away from the page, to disallow them to close their browser or go to another tab or type in another URL. So I had some alert popping up, and basically after an hour he came back and he said, well, this is probably your work. And I said, yep. So that's what I do. So what I'm going to talk about, monads, and one in particular, one that I like a lot, actually. It's a monad coming out of Scala, but don't worry, I'm not going to show you any Scala, just readable code. But so I'm going to talk about this one in particular. So imagine that you write code, and this is code I actually took from my company's code bases. It has a lot of if statements in there and stuff. I don't like if statements, basically. I don't like try-catch blocks either. So basically what we do is we sort of migrated from code like this, very traditional Java code written by a COBOL programmer. Then you get code like this, and it's sort of changed in a way that we write code like this. Now, that particular change is the one I'm going to be talking about. Of course, it looks a bit more functional, and functional programming, as we know, is very tough. But I would say that if you try to do this stuff, and of course, I think are you a Java developer? Oh, not a lot. Oh, so there's 3 of us now. And we're happy that we have Lambda expressions now too, since version whatever, 8 or something, right? You as C# developers, because you're probably all C# developers, or JavaScript developers, you'll laugh about that, but we haven't had in Java Lambda expressions for a long time. So this is it. So I'm going to do a very, very short introduction of programming and programming languages. It's mostly wrong. By the way, does anybody know what this is? This is supposed to be, yes. Right. You're right. Grace Hopper is one of my personal heroes. I actually have a picture of her hanging in my toilet. It's not a joke, it's true. So this is one of the first bugs ever recorded. There is an earlier one actually, but I figured it out only recently, so it's not in the slide deck. So we'll start off with Grace Hopper. As you see, Vice Admiral Grace Hopper. And she introduced COBOL to the world, right? And she also invented the word bug, and she did all other things. She wrote the first compiler and stuff. So this is COBOL. COBOL is a nice language. It looks a bit like this. This is even worse, by the way, than COBOL. This is COBOL in Dutch. Right, so very interesting code. Not much you can do about it. This is the way it is, right? And then we moved on. So in 1964, BASIC was invented, right? So in 1965, they go back to 1964, and they stay there forever. So then we got to BASIC, and slowly things picked up. Then a guy called Edsger Dijkstra, a very famous scientist from the Netherlands actually, he said, well, the goto statement is considered harmful. And he said, as it stands, it's just too primitive. It is too much an invitation to make a mess of one's program. So if you still have goto statements, none of you do, you're in trouble, right? So then we moved on to the 70s. Now in the 70s, we came to lambdas. And there were some people who wrote lambdas, the ultimate whatever. And then a lot of other stuff came after it, and they wrote a lot of these papers, but eventually lambdas became a very interesting thing. And they became especially popular because Java didn't have them for a long time, and the other normal programming languages did, right? So if you don't know what a lambda is, get into it. This is basically a definition. This comes out of the C# programming guide, by the way. A lambda expression is an anonymous function that you can use to create delegates or expression tree types. By using lambda expressions, you can write local functions that can be passed as arguments, which is very important, or returned as the value of a function call. So lambda expressions are particularly helpful for writing link query expressions. That is only a subset from what they're useful for. Basically, what you can do now is pass a method call, which you don't execute yet, as a parameter to a function where you can actually execute that particular lambda call inside of your function. Now that is an interesting thing to do. So you can actually delay the actual execution of the method you write. You don't have to pass in values to your functions. You can now pass in functions to your functions. And that makes a world of difference, right? So, and then of course you have to talk about pure functions, because we're now slowly moving towards, let's say, towards the monad theme that we're going to talk about. So a pure function, but first let me do some introduction about Haskell. So Haskell got invented at some point in time by a committee formed by Simon Peyton Jones, Paul Hudak, Philip Wadler, Aston Kutcher, and the People for the Ethical Treatment of Animals. That's not true, by the way, but not the last part. Anyway, so Haskell, does anybody of you write Haskell? Oh, cool, you must be the bright guys on the block, right? That's, I don't even know how to read Haskell, by the way. Anyway, so it has an interesting thing that says, well, a monad, first definition of monads, a monad is a monoid in the category of endofunctors. So what's the problem, right? I didn't know how to do this, right? So there we go. So a pure function, because this is where it's getting interesting, right? A pure function is a function without side effects. That means I pass in some parameters. It doesn't change the original parameters. It just work on the parameters and has a result. There is no side effect. So that means if you start logging stuff in your function, which most people do, if you start printing stuff or sending it to a database or whatever you do, are basically side effects of the pure thing that you want to calculate. They're also idempotent. It's like, for instance, if you calculate the cosinus of some value, it will always be the same result, right? It doesn't change if you pass in the same x. it also doesn't change the x value for you. Right? So that is basically what a pure function is. Now, pure functions are very interesting. Actually, thinking about it, you might say, I want to program in pure functions all the time because they have no side effects. That makes them much easier to test. It makes them easier to write too, by the way. But on the other side, we still need to print stuff and we need to log stuff and there's errors and there's if statements and all this rubbish that you might do during programming. That means you have to take care of that. Also, I'll already explain, I'm ahead of my own slide deck, is that they usually, or they're always idempotent, which means they don't change the values passed in, and the result is always the same, right? So, the question is, what if you want to write pure functions, basically, but you need to take care of all those side effects? How do you solve that? How do you put in the side effects? Now, that's where code gets messy. All of our code has this, right? You all have log statements somewhere in your code. Sometimes I break my own code by logging stuff, which sort of changed the behavior of the function I was logging from, right? You've all had that, right? No? I might be the only one then. Maybe you're better programmers than I. By the way, I've been writing code for 35 years now. That's basically the fun about this business, about this field, right? You keep on learning every day. You get better every day. I'm a slightly better programmer than I was yesterday. Well, not actually, because I didn't write any code today, but sort of, right? And imagine that for 35 years. Imagine how low I began, right? So how do you handle this stuff? Well, basically, that's where monads come in, right? You handle this stuff with monads. And then the question is, what on earth is a monad? Well, that's where I'm going to try to explain that to you, right? So basically, if you're non-Haskell or whatever, here, this is what Douglas Crockford said about this, right? Monads are amazing. They are simple things, almost trivially implemented, which is true. If you look at the code for a particular monad, whatever monad you have, it's fairly simple to understand. But using them or creating your own monads is a step up from that, right? So with enormous power to manage complexity, which is true. Actually, to be quite honest, I started using consciously started to use monads about 4 or 5 years ago in most of my code, and it basically changed the way I write my code. Big time. It's a huge change for me. It's actually, I would say, a different paradigm almost. And I'll try to explain. But the thing is, as Dr. Crockford explains, by understanding them is surprisingly difficult, and most people, once they have that aha moment, which you will get, they seem to lose the ability to explain them to others. That's why they are so secret, right? As soon as you understand them, you're unable to explain them to your coworkers. That makes you a better programmer than the rest, but you're unable to explain it to them, right? That's even worse. And the thing is, if you think you understand monads, there's always this, the Dunning-Kruger Effect, which is my most... I love this graph to death, actually. It's, if you start to learn something new, let's say monads, and you go away this afternoon, you think, oh, now I know everything about monads. You tried your own, you built your own, you use it, and you think, oh, I know everything there is to know about monads. Until suddenly, for some reason, there is more to it. You start reading about it, and you think, oh man, I didn't get this. Actually, I don't understand a bit about it. And then only after some time, it starts to make sense. It took me probably 4 months before I fully grasped the whole idea about what I was doing with these monads. A colleague of mine came up with them, and I started using them before I really actually understand the real value of this thing. And my favorite part of this graph is that point there, up above. You know what it's called? It's called Mount Stupid. For some reason, I love that phrase. So here we go. So there's a book on category theory, which is some very hard part in mathematics. So if you're not a mathematics major, this might not make any sense to you. I've read it like 5, 6 times. I don't understand a bit of it, right? So let me explain monads to you in a very, very simple way. So let's say you have something that you want to work on, some object that you want to do stuff on. Now, here's the thing. Monads consist of 3 different parts. Maybe more, but these are the most important parts. there's a unit function, as it's called. It's actually saying, so there's a box in this diagram, and the monad is actually the box. So you start off with putting something inside of the box. So the object that you actually want to work on in a pure way without side effects is the one you're going to put inside of the monad. So the monad is basically a box, right? Now, as soon as it's in the box, you want to do stuff with it, right? You want to actually manipulate the object which is inside of the box, but you want the box to take care of the side effects. So what you can do is actually pass in a function, a Lambda expression, to the box and say, could you please manipulate the object inside of you using this function? And then, of course, the object inside of the box gets a different color, or whatever you want to do with it. And then you can do another one, right? You can say you can pass in another function that works on the green ball. It doesn't necessarily work on the orange ball. It could be a green square that's now inside of it, anything. So you actually moved the object from being a, let's say, a person to a city, right? I use that example later on. And when you have a city object, you can actually move it towards a blue one, maybe a country object, depending on what you do. So it depends on the transformation that you put inside of the box that actually works on the object that you want to manipulate and gets a different result. And then the next step is you take it out of the box. So it's been manipulated, and the box handles the side effects. And then afterwards, you can take it out. This is basically how monads work. It's not difficult, right? Are you still here? Yeah, okay, you're on. So, what else is there? Well, to manipulate something, you have to pass in a function, right? So if there's an orange ball inside of your box, you want to pass it a function that transforms the orange ball to a green ball. So there's a map. Map is actually the same as bind, saying, okay, I pass in this function, this Lambda expression, that manipulates the orange ball and becomes a green ball. And you return the green ball in the box. Because map is a function of the box, right? And there's a second one, and it's usually called flat map. It doesn't necessarily need to in all languages, because if you would pass in a function that from an orange ball creates a green ball already in a box, this is the difficult part, I know. So if I would do that in this function, it would return actually a green ball in a box in a box. And you don't want that, because otherwise you would end up with, if you chain this with a green ball inside of 17 boxes. So what you do is you create a second function that, although this one returns the green ball in the box, it doesn't add a second box to it. So you just return the ball in the box. That means that you still have the box object that you can do the next map or flat map to. So you can actually chain this stuff. And by chaining it, it makes it very much more powerful. So you're looking a bit, well, blurred, but it is like, what is it, 4:30? It's actually 4:30. Wow, I have a biological clock. It doesn't work, but I have it. Anyway, so I'll show you a very simple example. Of course, I know this is in C#, and I know C# has the Elvis operator, but it's just a very simple example that you could use and do. Let's say I have 3 different classes, right? One of them is called person, and the person lives in a town, and the town sits in a country, and the country has a name. Basically it's a very, very simple example, I know. But you can do a lot of complicated stuff with it. Now, I used to write code like this, right? Like, okay, you know what? I pass in a person. If it isn't null, then I can ask for the town. So, and if the town isn't null, I can ask for the country. And then I would actually have to do another check to get the name, because the name can also be null. And if I want to manipulate the name somewhere else, it actually will crash, right? Now, this is very traditional code, and I know you now will write the Elvis operator to do this stuff, to check for nulls, but checking for nulls wasn't always there. Even worse, checking for nulls means that you're actually trying to solve the $1 billion mistake. Right? There is a guy who actually invented null. Can you believe that? And it's a guy called Tony Hoare, Sir Tony Hoare, by the way, and he said, I was designing the first comprehensive type system for references in object-oriented languages, ALGOL, and my goal was to ensure that all use of references would be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference. this is where we spend all our money, right? We check for, about half of our code is checking for null references, isn't it? Except if you do Haskell, of course, because that makes stuff different. So, and he actually named that his $1 billion mistake. I would say it cost much more than that, but let's assume it's $1 billion, right? So, what you could do is say, you could write your first monad. This wasn't my first, but it's an example. I call it the maybe class. And the maybe class handles null checks for me. So what you can see here, I'm going to use this. So it has, wow, this is cool, right? So it has a method called of, which is basically, so the maybe class is the box, right? So you put something inside of the box, which is of type T. For instance, this shirt. Anyway, so, and it returns the box that has the value inside of it. Well, this is not all of the code, by the way, but slightly more. But, and then there's a map function saying, okay, I have a function that transforms the T to a U, and it returns a maybe object with a U inside of it. All right? So you can pass in a function, and something else comes out of the function, and that's the new thing that's inside of your box. It has a second one, of course, where the function goes from T to a maybe U. So this function, and you require this to actually be able to do chaining, already returns a box. And you don't want a second box. So what this does is saying, you know what, I'm just going to invoke the function. That depends whether there's something in the box. If it isn't, I'll return the none, which is sort of a default thing. And otherwise, I'll just invoke the function. And by invoking the function, I return a new thing inside of a box, which is of type U. Right? So, oh, arrows, wow. Cool things you can do with PowerPoint, right? So, if you start using this stuff, you end up with code like this. Again, this is a stupid example, I know, but it sort of makes things very clear. So, here's a method that says, give me the country name, maybe. I put in a person, so I'm saying, please construct me a box. I'm going to quit this. Please construct me a box where there's a person inside of it. On that box, I call the map method, and I put in a Lambda expression, say, give me the town from that. And from that town, give me the country. And from that country, give me the name, and otherwise just put in an empty string. Now, so it sort of removes all of my null checks for me. So this is a class, the maybe class actually is a monad in some programming languages. Not in C#, of course, because we have the always operator. And this is a very, very straightforward, simple example of using monads. I'll give you some more complex ones. Again, we don't need it in C# anymore, but there's other languages, more primitive languages, that could do with a maybe monad. So other monads you're already using, as I said up front, you are probably already doing this without knowing it. So are there boxes that you can wrap around stuff you actually want to do? Yes, there's lots of stuff in there. Like in C#, for instance, you could say the select many thing, and most of the linked stuff in there is basically a monad around a collection of stuff that you can work on. Right? You can pass in a lambda, it transforms if you do a map or select many, whatever you do. It actually transforms to a new collection that you could work on. This is stuff you already know. Or maybe like the task class, right? The task class is used to be able to run async code. So it contains the async code. You can call it, and you can work on that when it comes back. That is stuff you already know. If you are a JavaScript programmer, who of you is a JavaScript programmer? So in JavaScript, you work with async code all the time, right? And there's a thing in JavaScript called a promise. Now, a promise is actually a monad. It's a monad that you use to handle async coding. And it either comes back, if you actually call code inside of a promise, it comes back with either a then or a catch, or depending on the, I'm using TypeScript, so it comes back like this, right? So the validate method that I have here returns a promise. On that promise, depending on what comes out of it, probably an account, I'm saying, well, it's probably an A here, but so I'm saying, you know, on this one, please save it through my repository. Now this repository, because this is my own code actually, this repository will go and go to a gateway, and that gateway will actually fire a REST request. So it comes back sometime with some answer, meaning it's now going to wait for the answer to come back. If it comes back and it's still okay, so it was fulfilled, meaning I expect this method to come back with an account. And then I can set it to my local variable that I'm working on and say, show some info, and if not, I'll end up here. So it means that this particular promise monad, which you're probably used to if you're doing JavaScript, actually, if one of these lines of code fails, it doesn't really execute the other ones. It goes straight into the catch. Well, it looks like that, but it doesn't actually, because it does execute the then methods. It's just saying that if I have an invalid result, or maybe I have an error inside of me, meaning I can skip the actual Lambda expression that is there and just pass it on to the next one. So it does that all the time. So if the first one fails, let's say this one fails, it actually goes down to here, but it does come through all of these statements, right? It just doesn't do anything. Are you still here? I know it's a tough topic for late in the afternoon, and then you can catch it and go on. I'll give you another example. Here's one I wrote recently, and I actually like it. I hate writing switch cases in any language, by the way. It doesn't matter whether that's in TypeScript, C#, Java, or whatever you do. I just don't like them. They can be much more compressed, I think. So I wrote something that I called the case monad, and guys on my team actually use this thing, much to my surprise. And it looks a bit different. So what it actually does, it handles cases, switch cases, right? So the switch case says, if this is true, then you need to execute that. If this is true, you need to execute that, etc., right? And there's maybe an otherwise or an else you have in the end. And this is basically it. This is the whole thing. So what I do is I create, I put anything inside of my box, which is the value that I want to switch upon, right? So maybe it's a string saying hello, and then I check for, if the string is hello, if the string is not hello, if the string whatever. And there's a with method saying, okay, here's a predicate. So it's basically a method that says, okay, the value that I have, which is basically the value inside of there, or you can check the value that's inside of there, and a Boolean needs to come out. If this becomes true, then you need to execute this one, and that's the value that you pass back. See? If it's not yet evaluated, and the predicate, which is here, this is this one, is actually evaluated to true, then I need to execute the f method, which is the second one here, and I put evaluated to true, and I return this, done. And because it changed, you can use it to actually write a case statement. Now, this might seem a bit weird, but if you look at the resulting code, it looks a bit like this. Now, to me, this is a much more, of course, you can put a return in front of it. I did here because I didn't need it. But this is typically something you can do with a monad like this. So I'm not saying that case statements are wrong, but they can be much more compressed. Also, what you could do is, what if some of these functions here actually would crash, right? If they would throw some sort of error or throwable or whatever you have, in whatever language you have, that would crash your switch statement. Now, what you could do inside of the with method, which I didn't, by the way, but I'm actually thinking of doing that, is saying, okay, if I evaluate this and it crashes, I need to put that in a try-catch block. So that means in my with, I'll go back one slide, if I can do that, yes. So in my with method, actually, I think in the current version of this, it actually has. It has a try-catch block around this, meaning that whatever I do with these predicates, it's sort of safe. That also means in all of this code, I don't need to check all that stuff, right? For any errors that you might try to catch or whatever, it all happens inside of the box. So the box handles that responsibility. It handles the side effect of dealing with try-catch blocks, if-then-else blocks, whatever you do. So this is another example of using monads in real life. And this is one you could probably figure out yourself how it works. I probably need to put it on my GitHub account, but I didn't. And this is one you can work on yourself. And it makes code more robust, I would say, because the side effects are always handled. You cannot forget it because it's not inside of your object, it's in the box. The box handles everything. So there's another one that I want to draw your attention to. So I tried to explain to you what a monad is, what it does. I showed you some examples from real life. So if you're lucky and you're a JavaScript developer, then you already have worked with this stuff, probably without knowing. So I'm trying to make it a bit more conscious to you. So there's another one, and this is the one I find very interesting because this is the one I actually made me change my way that I write code a lot. So a colleague of mine wrote an implementation in Java of something that comes out of Scala, which is called the try monad. And it really works well in any language that we work with. So, to continue a bit of history, here's a guy called Gerald Weinberg, very famous computer scientist, and he said, well, in 1975, right, he said, the if-then-else statement is considered harmful. Although the if-then-else constructor for flow of control is simple in some senses, and certainly superior to unrestricted go-to logic, so he's looking towards Edgar Dijkstra's paper, which was written some years before that, the indefinite replication of this structure leads to undesirable program constructs. You didn't think of that before, right? Because if statements, you use them all the time. I don't like them. You know why I don't like them? It's because of unit tests. Of course, you guys all write unit tests, right? You do. I'm not going to ask who doesn't, because that's... So the first time I asked... So I was in a conference in Poland a couple of weeks ago, and I asked, and there was only little people that actually did that. Of course, then I asked, who was born before 1970? And I had like 500 people in the room. I was the only one. But I write my unit test occasionally. And so the thing with unit tests is every if statement that you have in your code brings you two paths at least, right? That's where the trouble begins. With every if statement that you have, there's two paths that you need to test. The one that you want and the other one. So if you have two if statements, like the code in the start of this talk, that had like 4 if statements adjacent to each other, and you need to test all those paths, right? That makes testing a hell. So try to avoid that stuff as much as I can. Now, also, I don't like try-catch blocks. Try-catch blocks are just too much work for me. Of course, you will do that automatically in all your code, so it becomes robust and safe. I don't. I hate try-catch blocks, just basically. And then this guy on my team came up with, he said, you know what, in Scala, this is Scala, there's a thing called the try class. The try class handles that for you. It is a monad. And it's one of the most valuable that I've seen since. So basically what it does, it sort of handles try-catch blocks for you. So the code that you run inside of the try class, or the try class is actually the box, is very robust. And it's also chainable because all of these monads are chainable. And I'll show you how it works. So this is the definition of it, what it all has. So it has a map and a flat map. Most of the stuff that I already shown you. Now, this one is slightly more complicated than the other ones. I'll show you. So here's a very complex class diagram for it. You see, I've done all my UML thing. And this is most out of UML that I got these days, unfortunately. Now, so there's a try class, which is basically an abstract class. And two classes derive from it. It's the success class and the failure class. That means basically on any method that I call on this class, it returns either a failure or a success. But because they're both derived from the try class, they have the same interface. It means either one of them, I can actually still continue to chain other methods to it. Right? And that makes it a powerful thing. Let's show some code in here, right? So here's part of the try class. This is, by the way, another language. It's called Java. For those of you who do JavaScript, you probably don't distinguish between C# or Java. The biggest difference is they don't use capitals at the front of the first letter of your methods, right? Other than that, they're pretty much the same. No, they're not. Anyway, so here's a map method again and a flat map. I had to give them two different names because Java is not good at distinguishing between this signature and that signature, so I just gave them two different names. In C# I created a type class where both have the same name. It doesn't really matter. See, it's the one that says, okay, you pass in a T and you get back a U. And this one says you pass in a T and you get back a try of U. Both of these methods actually return a try of U. So this is the thing that allows you to chain. Now, they have something additional to that, is that if the Lambda expression that I pass in, that is executed inside the body of that map method, if that breaks, it fails, so it crashes, it returns some sort of exception. So the next thing I would have to do is I would say, okay, if there is an exception, this thing does not crash, basically, because you keep it, the map method has the actual try-catch block. There's only one of them in your code after that. So, but if there is an exception, I want to know, because I want to be able to recover from that. Now, how do you know that it recovers? Now, it does know because there is a slight difference in implementation from the success and the failure class. I'll show you. So this is the most complex part of the talk, and I'll probably have time to write some code too. So this is part of the success class. So the flat map method actually applies the function that you get back, and it returns it, unless it actually breaks, and there's some throwable or exception, whatever you might have. In that case, I'll return an instance of the failure class instead of an instance of the success class. So that means if the result of this method of calling the flat map is still a success, then the next line of code works on an instance of success, meaning I can do a next flat map. However, if for some reason that code breaks, an instance of failure is returned, and failure has a very different operational mode. So the recover, I don't need to recover anything because I am a success. Really nice, right? I'm going to say I'm a failure later on, but okay, now I'm a success. I don't need to recover from anything, so I can just return this. Right? So if I call a recover in my chained methods, and it's still a success, I don't need to do anything, just return and go to the next statement. However, if I am a failure, right, it's just the other way around. If I'm already a failure, that means in some of the previous lines in my chain, something has failed, meaning I've returned the failure object, the failure box, that's called that. I'm just going to return a new failure. And if I call it a recover, and I am a failure, that means I want to recover from something that went wrong earlier on in my code. I'm going to apply the function that I pull in, apply it, and return it. Now, this function either returns a t, so I'm in the end, or if it fails, I'm going to return another failure. And you might think, what on earth is he doing? Let me show you some code that actually does this. So here's an example. And this is what it looks. This used to be, I used to have the original code in here as well. It's a code block this big, right? And it's now only 6 or 7 lines of code. This is basically saying, so if I post something, I get an input object in here. I get the input object from it, and I create a node. So if this method fails, creating a node, for some reason, I don't know why it fails, it might fail, it will actually return a failure, which means the flat map method is called on the failure object. It doesn't do anything because it's already a failure. And it continues until it reaches the recover, and the recover will say, hey, you know what I'm going to do? I'm going to do this one as I try to recover from the failure I had earlier. In this case, I'm sending it back a bad request. But that is specifically if a validation exception occurred. If not, I have a general recover method, and basically what it does, it says, oh, you should throw an internal server error, and it returns an internal server error. If this one works right, and I can actually insert it into my component, this is coming from one of our microservices, then I say, you know what, I'm going to return create it and pass in some stuff, and that's it. And it basically ends here, because if I'm still a success here, that means the recovers actually don't do anything. I'm just getting the value out of it again and done. Right? Now, these 6 or 7 lines of code actually replace this block of code full of if-then else's, try catches, etc., etc. It makes our code really, really robust. It also makes it really easy to test. And you might think, does that work for me? Yes, it does. But you have to get used to it. So I wrote a C# implementation of it as well. This is the one that's on my GitHub account. We also have a TypeScript implementation of it. My current team rewrote it. This is TypeScript. And I'm still slightly improving on it, but it works really great. And you know what? I'll show you some examples from the code I do. I still have 12 minutes left, so I'll be able to do that. So are you still with me? Are you still, or is this thing, are you like, oh my God, when is this stuff over? And can't this guy shut up or whatever? So I'm going to make it worse. I'm going to show you some code. So first of all, let me start off. Oh, I hope this one still does work. Let me pull it out. Oh, it's on my back. So we're going to start with some Java, right? So I have a bunch of IntelliJs open. So I'm going to start at the top. This is one of our microservices, and you might say, oh, that's a bunch of code. Yes, it is. Well, it's one of the bigger ones. And what you see here is it actually has like a 4-layer architecture. Don't worry, it's not that complex as you might think. So basically, if a request comes in here, it starts off by validating the input. We have a class for that, doesn't really matter. And this validate actually returns a try. I'm not sure if you can see this. It returns a try of the search input. So it actually takes what comes in here and puts it inside of the box. It does some validation, and depending on whether the validation breaks or not, it will return a success or a failure. So that means I can actually do the next thing. Now, one of the methods that the try class has is a filter method. What the filter method does, it takes a predicate, and if I'm still a success, I execute the predicate. If that returns true, then I can continue. If it returns false, then it returns a failure. Right? That means if the filter fails, it actually boils down to the recover, one of the recover methods, and we'll check if it recovers. And then, if the filter still succeeds, I'm going to flat map to this method. So I'm going to execute this method on this particular class, and if that works, then I'm going to take the next step. If it doesn't work, I'll end up in one of the recovers. Right? So it removes all this if-then-else stuff. So I'm going to drill down to that particular method, which is a layer below that. And you can see that the code becomes easier here. So again, a layer beneath the resource class is my repository, and my repository should return a list of organizations, but we put that in a try as well. So we do that in every layer of our architecture. So that means the actual failure boils up, even from the lowest level of failures that we have, they all boil up to the same point where I only have one particular recover statement, which is in my top layer, in my resource class. That's the only place I actually have recover statements. All the other ones are just tries, and they return a failure or a success in any way that you execute. So if I go down another level, so there's probably, so what do I do? Find by, it's probably here. So the find by, this is actual code, right? So it goes down into the repository, find by code, bang, now I'm here. So, and then I'm a level lower again, and it goes into a gateway. And a gateway is something that actually talks to, in this particular case, probably a Mongo database. So I go into the gateway, and the gateway does actually construct the first, so this is decompiled code because it's in our libraries, and it actually constructs the actual first try in the chain, right? But every exception that occurs somewhere on the chain between getting from the actual request that comes in to the database and back, all comes back into the resource class where we can handle it in one single call, namely the recover that I have there. Now that is, when I first started doing this, I figured out, wow, this is pretty cool stuff. Now this is a fairly complex piece of code, and I'll just show you because it's the first one that came to mind, but I'll show you in TypeScript as well. So, in TypeScript, where's my TypeScript library? There, right? So I was writing these tests earlier. I'll write a new test for you. So I have a same implementation of the try class in TypeScript. I'll show you. It's somewhere in our libraries. So here's the actual class, and it has an is success or an is failure. So you can ask it, are you a success or are you a failure? Something you need to ask. And it's differently implemented in the success and in the failure classes, of course. And then there's the map and the flat map that take a function and return a try of you. And there's the recover functions and some else functions, and you can get the value out of it, and that's about it. Right? So this is basically my try class. If you boil down, for some reason, all three of them are in the same file, which doesn't need to be. So here's the success class. It basically inherits from the try class and overrides a bunch of these methods. Like the map and the flat map, they're actually implemented here, but you will see in the recover class, in the success class, that the recover methods don't do anything basically. They just return the same instance of success, and then you can take it on from there. Now, the failure class is just the other way around, of course, because where is it? Oh, here it is. So it returns true on the is failure, and it returns false on the is success. And the flat maps, they return a new failure, and then the recover methods actually execute the method that you pass in, returning an error, and then you continue to move from there. So this is how it works. I'll show you. I'll write some tests. That's the easier thing to do. So in my test, I created this very stupid situation where I have a person class here. It has a constructor. This is one of the things I like about TypeScript, is that if I have, in my constructor, I can have a public field, which is actually become, I don't have to declare it, and it's just there, right? I like that a lot. If you're not used to this, it looks weird. So, and I have a title property that says, oh, give me the title. And the title says, if there's no name in it, throw an error. If it is, say hi, blah, 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 whatever, right? Cool. Then I have a foo class, which has two statics saying I have a property called no name and a property called sender. That's me. Right, so this is my code. I'm going to test the code, right? I'm going to write a new test, see what happens. First of all, let me write a test that is called whatever. See, it doesn't really matter what name it has. So let me do one thing at a time. Let's say I'm going to do an assert saying equals, what shall I do? foo.sender.name to lowercase, and it should equal my name in lowercase, right? Yeah? I'm actually gonna kill this one. I just wrote it an hour ago. So let me run that test for you, right? You should expect that this works. Go to here, run the test. Can you see this? Yeah, it's there, right? Bang, it passes. Really cool, right? But the thing is, if I would say, create me an instance of no name. Now, no name is a person object without a name, meaning that if I create it and I ask for its name, it probably crashes, right? So I'll put in no name now. Let's run the test again, see what happens. Bang. Probably fails, right? I hope it does. See, I cannot read the property to lowercase of undefined because the name is not defined, right? So let's try something else now. Let's say, I'm going to say try of foo.noname, right? That's my object without a name. And I'm going to map that saying, okay, so what is in here now is the person object inside of the try box, right? So I can say, I can name it P for person. So you can actually see that there's an any in it. Why is there an any in it? Because this is not a Lambda expression. That helps, right? Now it's probably a person. It's a person. You never should write code on stage, right? You know that. And so what do I want to do? So I want to get the name of that one, which is still okay, but it's undefined. And from that, let's put it easy. Let's say map. Now I have the name, meaning I can do actually name dot to lowercase, right? Now we saw previously that this breaks. Now let me put that some let result. So if you're a Java programmer, we now in version 10, whatever it is, we have var. Okay, people who don't write Java, you could laugh at that, but so it's let in TypeScript, right? So I now have a result thing, and I could say, do me the result, and you know what? I don't know what it is, but it's probably empty. So I cannot do that. You know what? It's undefined. Is it? I hope so. So what I did now is saying, give me an instance of foo called no name. It doesn't have a name. I'm going to ask for the name, which is undefined, and I call the lowercase method on that. Now, as you saw in my previous test, that breaks, right? It's right on screen here. So now I've put it inside of the try, which means the actual execution of the end to lowercase is not done here, but it's done inside of my box, meaning the box handles the try catch. So I hope that I probably did something wrong. Yeah, I probably did, because it actually returns a try, right? Not you should have helped me with that. But what I now can do is say, are you a failure? And it should say true, right? Because I have an instance of failure. And if I do this, now I hope that my test actually passes. I'm still good. Wow. So I know this was a very simple example of that, but given the point in time that we are during this talk, this is about the example I can give you. I actually want to put, where's my microphone? I actually want to put the try class in TypeScript on my GitHub, but I haven't done that yet. So let me wrap this up by saying, I have to do a retrospective, right? So for all of you people doing Agile, I'll be doing a talk about Agile tomorrow with Kim, which is a fun talk. This is the second time we're going to do this. And we're totally going to bash on Agile. I've been doing Agile for 20 years, so I can do that, right? So basically, in retrospective, what about monads? Monads are fun. They seem complex. You have to get used to it. Be aware of the Dunning-Kruger Effect. You'll get up on Mind Stupid and think you know everything about it. You don't. I don't, right? I'm somewhere coming back from that. And there's lots of stuff you can do with it. It removes most side effects, and it's not just a try class, but you can use any monad that you can think of handling side effects. For instance, logging, you could handle that with a monad if you want to. I'm not sure if I would do that. Oh, we have done it, by the way. So the try class, it removes all your try catch blocks, your if then else blocks, and it totally changes the way you code. It will take some time. It will take you maybe a couple of months, maybe half a year, before you get used to it. First time you're trying the try class, you will try it in one location and then still pass back the original value. And only after a while you will realize that chaining it from level to level in your code base, in your architecture, actually makes your code even more robust. So it is a very interesting concept. Please give it a try. Oh, that's a bad joke. I just made it up. And help you stop all this stuff. So last slide, I have some resources on this stuff. There's tons of resources. Most of them are very unreadable, very complex, but just give it a try to yourself and see what you can do with it. And there's some videos of this talk as well, and some of my code. Here's my website, my GitHub account. I'll try to put up the TypeScript monads that I have as soon as I've written some tests for it. And thank you all for being here. I ran slightly over time, but only 2 minutes, which is my personal record. So thank you for indulging me this late in the afternoon talking about this difficult subject. I hope you have a great conference, and see you at beer.